So NASA just dropped a new alert about this interstellar comet. And honestly, I need to talk about this because what they're seeing now is genuinely unsettling. Every single time we think we've got a handle on how this thing behaves, new data comes in and basically tells us we were wrong. Again, if you've been following along with me on this journey, you know that this comet has been doing strange things for a while now. But what showed up in the observations today might be the clearest sign yet that something fundamental is changing inside this object. And I'm not being dramatic here, the data is actually kind of alarming. Let me walk you through what happened. Before we continue, if this has your attention, you can subscribe, turn on notifications, and hit like anytime. And for the best viewing, switch to full screen and enjoy what's coming next. So today started pretty normally for the observation teams. They were doing what they always do, comparing images from different days to track how the comet is evolving. They line up yesterday's images next to today's using the same instruments, same filters, same tracking methods. Standard procedure, right? At first glance, everything looked like the usual weirdness we've come to expect from this comet. You've got your bright inner coma, some structured jets shooting out, a tail that curves slightly, nothing too shocking. But then they did something called a blink comparison. This is where you rapidly flip back and forth between two images, two spot changes that might be too subtle to see when you're just looking at them side by side, and the moment they started flipping between yesterday and today, something immediately jumped out at them. The center had changed, and not in a subtle way. In yesterday's image, the inner coma had one clear bright spot right in the middle. One core, one source of light sitting there in the center of all that glowing material. Clean and simple. But in today's image, that single bright spot isn't there anymore. Instead, what they're seeing is this stretched out shape, almost like a peanut. There are two brightness peaks now, incredibly close together, sitting inside the same fuzzy halo of material. They're not fully separated. It doesn't look like two distinct comets flying in formation, but it's definitely not one simple core anymore either. Now, the first thing any good scientist does when they see something weird like this is question whether it's even real. Maybe it's just an artifact from how the images were processed. Maybe the telescope tracking was slightly off. Maybe it was some weird atmospheric distortion that made one bright spot look like two. There are a million ways data can play tricks on you, so they went back and reprocessed everything from scratch. Different alignment techniques, different ways of combining the images, different filters. They tried everything they could think of to make that peanut shape go away. It didn't go away. Then they reached out to another observatory that had been looking at the comet around the same time, completely independently. Different telescope, different location, different team, same peanut shape, same elongated double-peaked core. At that point, they had to accept what they were seeing. This isn't an artifact. This isn't a processing error. The inner structure of this comet has genuinely changed, and it now looks like it's trying to become two separate things. But wait, because it gets even more interesting when they started looking at the light curve data, which is basically a graph of how the comet's brightness changes over time as it rotates. They found something that matches up almost perfectly with what the images are showing. Previously, each time the comet completed one full rotation, you'd see one main peak in brightness, maybe with a smaller secondary bump. That made sense if there was one dominant active region on the surface that was firing off jets of material. But in today's data, that secondary bump isn't secondary anymore. It's almost as bright as the main peak. Now, what you're getting is two major spikes of light with each rotation, separated by almost exactly half a turn. Think about what that means for a second. If you have two major sources of brightness and they're positioned on opposite sides of the object, then, as it spins, each one takes turns pointing toward us. First one comes around, you get a big spike in brightness. Half a rotation later, the other one swings into view and you get another big spike. You could potentially get this pattern without the comet actually breaking apart. Maybe it just has two really active regions on opposite sides. But here's the thing. It's really hard to get this kind of pattern if nothing inside the object has fundamentally changed. Something is different now compared to what it was before, and then there's the orbital data, which adds another layer to this whole puzzle. NASA's tracking centers run these incredibly precise calculations to figure out exactly where the comet is and where it's going. But comets aren't like asteroids. Asteroids mostly just follow simple gravitational paths. Comets, on the other hand, have jets of gas and dust shooting out of them, and those jets actually push on the comet, changing its trajectory slightly. Scientists call these non-gravitational forces, and you have to account for them to accurately predict where a comet will be. So when they ran today's position data through their orbital models, they had to update these non-gravitational terms again. And this time, something new showed up in the solution. Instead of finding one dominant direction where the thrust is coming from, with just a bit of random noise around it, the computer model now prefers a more complex setup. There's still a primary push in one direction, but now there's also a second, weaker push coming from a slightly different direction. strong enough that you can't just ignore it anymore. It's almost like the comet suddenly has two engines instead of one, a main engine and a secondary engine, pointing in a slightly different direction. And that's exactly what you'd expect if different. Parts of the nucleus are now firing off jets independently, or, if you have two pieces that are still close together, but venting material in slightly different directions. So let's take a step back and look at the complete picture of what today's data is telling us. The images show an elongated, double-peaked brightness distribution in the core. The light curve shows two equal brightness peaks per rotation instead of one dominant peak. The orbital dynamics show thrust coming from two different directions instead of one clean push. All three pieces of evidence are pointing toward the same conclusion. Something has changed in the fundamental structure of this comet's core. It's not just the coma looking different. It's not just the tail shifting around. The core itself is now behaving like there are two distinct sources of activity instead of one. So what could actually be happening inside this thing? One possibility is that we're watching the nucleus enter what scientists call a deep structural failure phase. Let me paint you a picture of what that might mean. Imagine you've got this ancient chunk of ice and rock that's been wandering through interstellar space for who knows how long. It's porous, full of little cracks and weak spots. Then it comes screaming into our solar system and gets absolutely hammered by the sun's heat. It starts venting violently as ice inside turns to gas. Its rotation rate starts changing because all those jets are pushing on it unevenly. Inside, you've got ice melting, refreezing, melting again, and all that freeze-thaw action is putting enormous stress on the material. At some point, those internal cracks don't just widen a little bit. They connect, they form pathways, and the nucleus can start to literally stretch along one of those planes of weakness. You end up with two lobes that are still physically connected, but they're starting to pull apart from each other. From our perspective here on Earth, looking through our telescopes, that would look exactly like what NASA is seeing, a peanut-shaped core, two brightness peaks, because you've got two lobes catching sunlight, two different contributions to the thrust, because each lobe is venting in a slightly different direction. But there's another possibility that doesn't involve the comet actually breaking apart, at least not yet. Maybe what we're seeing is still a single nucleus, but it's developed to extremely active venting regions on opposite sides. In this scenario, the material isn't splitting into two pieces. It's just that the activity has become so heavily concentrated at two specific spots that, from our viewpoint, the coma behaves as if there are two separate sources. The light curve doesn't really care whether it's looking at one cracked rock or two almost separate chunks. It just responds to where the bright jets of gas and dust are coming from. Same with the images. If you've got two intense venting regions, they'll create two brightness peaks, regardless of whether they're on one object or two. Either way, and this is the important part, this is not what a stable comet looks like when it's heading back out toward the outer solar system. A stable comet should show one dominant rotation period that stays consistent, one main active zone that gradually fades as it gets farther from the sun, and gentle, predictable changes in brightness as the ice sublimates away. That's normal comet behavior. What today's data is showing is the opposite of that. Two big brightness pulses instead of one, two apparent cores instead of one, two thrust components instead of one unified push. Everything's doubled, and that doubling happens suddenly. That's why NASA issued this as a significant alert, not just a routine update or minor tweak to the data. This represents a step change in how this object is behaving. It crossed some kind of threshold. Now, here's what's going to be absolutely critical to watch over the next few days and weeks. If those two brightness peaks start drifting further apart in the images, if that peanut shape stretches out into more of a dumbbell shape, if the light curve starts showing small timing differences between the two pulses, or if the orbital model needs even more complex thrust parameters to match the observations, then we'll know we're watching the early stages of an actual physical breakup. This would be huge. By the way, we've never observed an interstellar object breaking apart. We've seen comets from our own solar system split, sure, but those are objects we understand relatively well. They formed in our neighborhood. We know what they're made of. An interstellar comet breaking up would give us an unprecedented look at the internal structure and composition of material from another star system. It's the kind of opportunity that comes along maybe once in a lifetime. On the other hand, if the pattern collapses back over the next few observations, if those two peaks merge together again, if the coma rounds out and goes back to looking like one unified structure, then maybe this was just a brief violent rearrangement. Maybe there was some kind of internal collapse or sudden outgassing event that temporarily made it look like two things. But the nucleus managed to hold itself together through it. Comets can be surprisingly resilient sometimes. They can go through these dramatic events and come out the other side still in one piece. So we can't rule that out. But here's what makes today's alert significant, regardless of which scenario plays out. Before today, we could still reasonably describe this comet as weird but fundamentally singular. Strange behavior, sure, but one object. After today, the data is clearly telling us that, At a minimum, it's acting like more than one thing at its core, whether it's one object with two distinct active regions or two objects still bound together. The behavior has crossed into new territory. And you know what makes this even more fascinating? This comet has been full of surprises from the very beginning. Every time the teams think they've figured out its pattern, the next set of observations comes in and changes the story. It's been frustrating for the scientists, I'm sure, but from a pure discovery standpoint, it's incredible. We're watching something unprecedented unfold in real time. Man object from another star system with a completely different formation history than anything in our solar system, putting on a show as it reacts to our sun's heat in ways we've never quite seen before. The fact that it keeps changing, keeps evolving, keeps surprising us tells us that we still have so much to learn about how these objects work. Every change, every new weird thing it does, is a clue about its internal structure, its composition, where it came from, what it's made of. So what happens next? Well, observatories around the world are going to be watching this thing like hawks. Every clear night, every chance they get, they'll be taking images, measuring brightness, tracking its position. The data is going to come in fast, and each new observation will either confirm this double-core pattern or show us something different. If this is the beginning of a breakup, we might see those two components separate more clearly over the coming days. We might see them develop independent tails. We might see them start to drift apart in their orbits. That would be spectacular honestly, though also kind of sad in a way. We'd be watching this interstellar visitor literally tear itself apart. If it's not breaking a pith, it somehow stabilizes or merges back into one clear object. That would be fascinating too. It would tell us that whatever internal event caused this double peak appearance was survivable, that the nucleus is more cohesive than it appeared in today's data. Either way, we're at a pivotal moment in this object's journey through our solar system. Today's observations represent a clear dividing line, before and after, what it was versus what it's becoming. And that's what makes this so compelling to follow. We don't know the ending yet. We're all watching this story unfold together in real time as the data comes in. Every day could bring confirmation that it's breaking apart, evidence that it's holding together, or something completely unexpected that no one predicted. This is science at its most exciting, not the stuff you read about in textbooks years after it happened, but the raw, unfolding discovery where nobody knows what's coming next, where the experts are just as surprised as everyone else when new data drops. So yeah, that's where we are with this interstellar comet right now. The core signal has changed. It's showing signs of being two things instead of one. And over the next days and weeks, we're going to find out whether this is the beginning of something dramatic or just another strange phase in the life of the weirdest comet anyone's ever studied. Whatever happens, I'll be watching, because with this object, every time NASA takes another look, it doesn't just look different, it fundamentally behaves differently, too, and that's what makes it so impossibly fascinating.